Dear students, welcome to our practical class on computation of climate change. Computation of climate change. This is the basic course. So I cover as far as computation of climate change is concerned. I confine myself to fundamental course where a first year or second year students in the introductory agrometeorology and climate change should learn only. Now, what is the definition or meaning of computation first? Use of computer or calculating by applying the material or software that is available in the computer. That is what computation. Now, there is one word called as algorithms. In the basics, in the school days, you must have heard algorithms. Algorithms, best example of an algorithm is what I used to teach my UG students. Is the best example for an algorithm is preparing a recipe in your home by yourself. How you prepare a recipe? You take some material, maybe a ketchup or something called as tomato soup or something like that. You add relevant equivalent quantity of water or somewhere, what are the directions given there. Then what you do, you add some more ingredient which would increase your or enhance the taste, and finally, as per the rules, as per the directions that are given in the preparation of the recipe by that particular company, you just warm it and then you drink it. So similarly, algorithms are like recipes only. That means there are set rules, there are certain procedures, and you allow some process. There are some set rules, there are some set equations. You allow the process, then it will solve certain problems. So in the climate change, as far as climate change is goes, I am not going beyond climate change. Now, as far as the uses of algorithms are concerned, there are innumerable uses, but as far as climate change is concerned, the algorithms are used generally for sampling the rare events of climate or weather. Sampling the rare events of climate or weather. Estimating the probability of extreme events. Extreme events means heat waves, cold waves, heavy rainfall, a thunderstorm, a super cyclone, like that. Okay. Now, the third use of algorithms in climate change are some algorithms are used in to help unpredicted or difficult to predict weather events. Okay, that's what. Now, actually studying extreme events and how they evolve in a changing climate is one of the most important current scientific challenges. How extreme events are occurring, how often they may reoccur. It is a challenge to the agrometeorologist. We confine our class to only agrometeorology and climate change as far as algorithms or computation is concerned, not beyond that. Okay, simple basics only. Now here, algorithms also help in the manner of evolving of cold and heat waves based on statistical physics. Based on statistical physics, how heat waves and cold waves are evolving and reoccurring. So that also is possible with algorithms. Now, just to sum up what we learned so far, what is computation, what is algorithm, what are the uses. That's what, this is the basic you should learn in the basic course. Now, so even though this is a basic course, all my beloved students should understand one basic thing. What is a climate system with reference to use of either computers or algorithms or statistics or physical statistics or dynamic statistics, whatever it may be. Okay. What is the how we should see the climate system. Now, please write this point. This bit will come in the JRF, SRF. Please write this point. The climate belongs to, please write, the climate belongs to a class of this is very important. The climate belongs to a class of non-equilibrium. The climate belongs to a class of non-equilibrium forced and dissipative systems. Forced and dissipative systems. So this is the thing. The meaning is, climate is a non-equilibrium. Stable, unstable, neutral, whatnot. So these are all the things that we have already discussed in the micrometeorology. Climate is a system which is a non-equilibrium, forced, and finally a dissipating system. It is not static. So this is how we view as far as computation of climate change is concerned. Then we apply algorithm. Then we apply physical statistics, what are different modes that in the next few minutes we try to understand. Here, okay, now in the climate change, what are the things that we should calculate in the climate change? Basically, now here, okay, after the usable calculation of climate change, what are the things that we should calculate for the climate change? Number one, CO2 accepted. Number two, temperature, either increase or decrease the temperature. Now, global warming and storms and global warming and extreme weather. This is substance for the basic course. We should know how to calculate when carbon dioxide is increasing, when carbon dioxide is doubled, when temperature is increasing, what temperature, daytime temperature or nighttime temperature. Warming. What is the warming? Warming with reference to thunderstorms. Warming with reference to extreme events. Warming means energy. Energy is there. Extreme events go on happening. So how to calculate? Just the basics only we try to understand. Not any advanced thing. Basics. Now please write if your valuable time permits. First I would like to tell you, when a small increase in CO2 content, when there is a small increase in CO2 content in the atmosphere, it makes a critical difference to actual global temperature of the earth. When there is a small increase in the ppm of CO2, it increases the global surface temperature. What is global surface temperature? Both lithosphere and hydrosphere. I repeat once again. When there is a small increase in the CO2, that increases the surface temperature of the globe. What is the surface temperature of the globe? Not only land and water. So this is the basis. How it can be calculated? Just very simple. Derivation, IPCC, Intergovernmental Panel on Climate Change, use this equation. What is the equation? Delta F is equal to delta F. Please all of you write delta F is equal to 5.35. Delta F is equal to 5.35 log n C by C0. Log n C by C0. The simplest equation. What is delta T? What is C? What is C0? That I will tell. What is 5.3? Everything I will tell. Now, this equation gives the increase in the heat flux density. Delta F is equal to heat flux density. Heat means energy. Flux means flow. Density with what density? Okay. Whether you use 4 years law of micrometeorology we studied. Okay, the thermal conductivity, thermal diffusivity, specific heat capacity, all those things I have elaborately discussed in the theory. Now delta F is the heat flux density, delta F. Then it is in watts per meter square. Heat flux flow, watts per meter square. That's it. When CO2 concentration increases from C0 to C, C0 initial level condition. C0 is condition. C0 to C. That means delta F change in the heat flux density is equal to 5.35 log n. Okay. Log C by C0. C is the estimating, C0 is the initial condition. So for the derivation 1, it uses the equation derived from the heat transfer equation. Just simple heat transfer equation. What is the simple heat transfer? Delta T is equal to 5.35 log C. Now, in the second derivation, the same principle is used. It also includes the derivation of basic equation, setting the initial condition. Setting the initial, that's what I told half minute back. Delta F, change in the heat flux is equal to 5.35 into log, okay, natural log, okay, C by C0. It is a condition. What is the basic equation? Log C. Log n C, otherwise log n C, okay, that's what, okay, 5.35 log n C and what. Now, what is the condition when we go for condition? C by C0. C is the final thing what we wanted, C0 is the initial. So this is how we calculate the temperature, calculation of the temperature, so CO2. When CO2 is increasing, it increases the global temperature. Basic equation is equal to delta F. Flux density, heat flux density is equal to, change in the heat flux density is equal to 5.35 Ln, that's what Ln C. In the conditional, C by C0, that's it. Now, second, let's go to the second one, calculation of derivation of temperature increase in the equation. Derivation of temperature in the equation, okay, temperature. Second thing is temperature. Daytime, nighttime time. That's what we discussed in the next class. Now, so before that, you should also know that calculation of CO2 flux density and okay, comparison with other non-condensing greenhouse gases that maintain a temperature structure for the atmosphere. So usually, when we are calculating delta F is equal to 5.35 Ln C or delta F is equal to 5.35 Ln C by C0. What are all these things? Conditional. C0 is the conditional. So, for all these things, we understand how an increase in the ppm of CO2 is increasing the global temperature. That is the equation. Now, what is our computation of climate change? That you should know basically. This is very simple, very even a 10th class student can understand this one. Am I right? No. Let us go to temperature. How temperature is calculated? Either increase or decrease. Simple equation I will tell. Delta T is equal to 1.66 Ln C by C0. Delta T is equal to 1.66 Ln C by C0. This equation gives the temperature increase. Delta T in degrees centigrade when CO2 concentration increase from C0 to C. Delta T, there delta F. Simple. Here, instead of 5.35, we give 1.66 and Ln C by C0. This is how temperature is calculated. Now, calculation of temperature increase for doubling CO2. For example, CO2 is doubled in a field experiment. You are doubling CO2. Then what will happen? So, calculation of the temperature increase for instant doubling of atmospheric CO2 content when there is no feedback from other sources and there is a feedback from other sources. What is other sources? CO2 in general, CO2, hydrofluorocarbons, perfluorocarbons, carbon monoxide, carbon dioxide, all these things from different sources enters into the atmosphere. Am I right? Now, this particular CO2 from main crops, for example, crops only, with reference to influence of, we wanted to study the influence of CO2 on the crop. What will happen? There, we don't take many feedbacks now. So, feedback from a change in water vapor capacity due to change in temperature, evaluation of the temperature increase for instant doubling of atmospheric to content when all feedbacks are included. There are two conditions. See, temperature increases, the CO2 increases in the atmosphere. That is the basic thing. There is no doubt about it. Now, we take from what are the main sources of CO2? Feedback. So many sources of CO2. So, for these two, yes, the same temperature equation. Delta T is equal to 1.66 into, okay, log n Ln C by C0. Okay, this is how we can do it. Of course, global warming and storm. Global warming and storm. Global warming and extreme weather. Okay, so why the strongest storms driven by latent heat will become more powerful as a result of global warming? Latent heat, okay, strongest influence on the global cause of storms is the latent heat. Why? The strongest storms, when there is more of latent heat, there is a strongest storm. Why? Secondly, global warming and extreme weather. Why a small increase in global surface temperature can mean an increase in the extreme weather? Why there is a small increase in the global surface temperature? Before that, there is a small increase in the CO2 ppm. that small increase in the CO2 pp because a small increase in the global temperature, either lithosphere or hydrosphere, okay, or both, okay, why the extreme events are occurring. So for these the computation is very simple. We calculate CO2 enhancement for CO2 initial C by C0 by C by C0. So that is what? Delta T. Okay, delta F, that's what we call it as far as CO2 is. Delta T is concerned, we use the same equation for this particular change in the temperature and also global warming and storms, global warming and weather. Finally, in 1 minute, I would like to impress upon you what are the models for evaluating the climate change. This is very interesting. There are different models. Simplest model I will tell. Everybody cannot go to Himalayas. If Himalayas are put in a 1 meter paper in a paint, you can see that is a model. It is a small imitation of the reality. So models, what are the models? Innumerable models. Say for example, in Agron, I always say to my basic course students that harvest index is a best model. Harvest index, okay, is the best model. Or how a crop had grown from seed germination to emergence to completion of the vegetative stage. Commonly 35 days it will take. So it is a model. When it becomes a model with reference to nutrients, a model. With reference to the outside temperature, a model. With reference to soil temperature, a model. A combination of all these things also can be a model. So, for climate change, I would like to impress upon you, just there are 3 basic models. Just for your academic interest only, you need not concentrate much on the what are the processes involved. That is algorithms involved in this. Just forget this is the basic course. Now, the first one is the conceptual or theoretical concept. First model is conceptual or theoretical concept. Second thing is the small scale quantitative simulation models. Small scale quantitative simulation models. So system scale, that is the bigger scale. Small scale, bigger scale, otherwise system scale quantitative modeling. So these are the basic modeling approaches used for computation of climate change. So this is what I would like to share with you. For example, what is the computational theoretical concept? Say in an area, in an area your agriculture college is located, in a month, this much rainfall is supposed to occur, 30 years average. But that has not occurred, what should happen? What will happen? That has more occurred, okay, what will happen? This is a conceptual or theory. Small scale models are statistical or mechanistic models, large scale, bigger scale, statistical, mechanistic, empirical, or a combination. This is a large scale. Statistical, mechanistic, scholastic, different models I discussed in the initial theory class. Same models we apply in the large scale simulation models for the climate change. So this is what I would like to share with you as far as the computation of climate change is concerned. Thanking you for your patient hearing.